If right now you stepped outside and looked up at the night sky, an ancient question would quietly rise in your mind, one that has never truly been answered. How vast is the universe? And how long does time really last? This is not a question born of modern science. It is a question humans have carried since before we had written language, since the first fires were lit against the darkness. No matter the era, we look upward with the same feeling: curiosity, smallness, and a subtle sense of unease. The universe contains hundreds of billions of galaxies, each holding hundreds of billions of stars, and yet within that immensity, humanity exists on a single small planet, orbiting an ordinary star located on the quiet outskirts of an unremarkable galaxy. The distances between stars are so immense that if we were to shrink them down, most of the universe would be nothing but empty space. And when we speak of deep time, we are not simply talking about millions or billions of years. We are describing a scale of time that escapes human intuition entirely. A flow in which past, present, and future no longer behave the way we expect. A realm where the idea of a human lifetime becomes almost impossibly fragile. If you enjoy science told slowly and calmly, stories that help you understand the universe while allowing your mind to settle and rest, you're welcome to subscribe. Here we explore the cosmos at a gentle pace, guided by curiosity rather than urgency. From this small point in space, we begin a journey toward the farthest reaches of the universe and the deepest reaches of time. When we imagine space, we often picture a vast, silent emptiness. A black room stretching endlessly in all directions, waiting for stars, planets, and galaxies to be placed inside it. This image feels natural, almost intuitive, but it is also deeply misleading. The universe is not a quiet container that we step into. It is not a stage on which matter simply sits. Space itself is an active structure, constantly changing, constantly responding to what exists within it. Matter bends it. Energy stirs it. Time flows through it in ways that depend on motion and gravity. Space is not passive. It participates. This idea can feel unsettling at first because our everyday experience offers no clear comparison. On Earth, space feels stable. Rooms do not stretch. Distances do not shift while we sleep. Time seems to move at a steady pace, indifferent to where we stand or how fast we travel. But the universe does not operate according to human-scale intuition. It never has. In modern physics, space and time are woven together into a single fabric of often called space-time. This fabric can stretch, curve, and ripple. Massive objects like stars and galaxies do not simply exist within space. They shape it. When a star forms, when a planet orbits, when two black holes merge, space-time itself responds. The universe is not still. Even in its quietest regions, it is never truly at rest. This is why the idea of a boundary to space is so difficult to define. We often ask where the universe ends, as if there were a wall at the edge, a final border beyond which nothing exists. But the true limit of space is not a physical barrier. It is a limit imposed by light and time. Light travels at a finite speed. No matter how powerful our telescopes become, they can only collect light that has had enough time to reach us. The farther we look, the farther back in time we see. Eventually, we reach a point where the universe was so young, so dense, that light could not travel freely. Beyond that horizon, there may be more universe, perhaps vastly more. But it remains beyond observation, not because it is absent, but because it is unreachable. Space rarely gives us simple answers. What we can observe is called the observable universe. It is not the entire cosmos. It is merely the portion whose light has arrived here since the beginning of cosmic expansion. The universe may extend far beyond this limit, continuing smoothly without edges or interruptions. Or it may have a shape that our minds are not equipped to visualize. Either way, the boundary we encounter is not a wall, it is a moment in time. Another idea that challenges intuition is how empty the universe truly is. We speak of galaxies filled with stars, nebulae glowing with gas, clusters containing thousands of galaxies bound together by gravity. And yet when we examine the universe by volume, almost all of it is empty space. The distances between stars are enormous. Even within a galaxy, stars are separated by trillions of kilometers. If the sun were the size of a grain of sand, the nearest star would be miles away. Between galaxies, the emptiness becomes even more profound. Entire regions of space contain almost no matter at all. Only a faint whisper of particles drifting through darkness. Silence is also a kind of data. This vast emptiness is not a flaw or an accident. It is a natural outcome of how the universe formed and expanded. After the early universe cooled, matter began to clump under gravity, forming stars and galaxies. But gravity works slowly on large scales. It pulls matter together in certain regions while leaving others nearly untouched. Over billions of years, this process created a universe that is both richly structured and overwhelmingly sparse. From a human perspective, this sparseness feels lonely. We tend to imagine space as crowded with destinations waiting to be visited. In reality, most journeys between stars would involve traveling through near-perfect emptiness for years, decades, or longer. There are no landmarks along the way, no reference points, just motion through a structure that does not announce itself. And yet, this emptiness is what makes the universe readable. If matter were evenly spread everywhere, stars would not shine as clearly. Galaxies would blur into one another. Patterns would be harder to detect. The very scarcity of matter allows structure to emerge. It allows numbers to mean something. Numbers whisper more than they speak. When we step back and look at the universe as it truly is, we begin to see that space is not something we move through like air or water. It is something we are part of. It shapes our motion, our clocks, our observations, and even our sense of what is possible. We are not standing outside the universe, looking in. We are embedded within a dynamic, evolving structure that has been unfolding for billions of years before we arrived, and will continue long after we are gone. And perhaps that is the quiet lesson of this first step. Space is not empty, and it is not waiting. It is already in motion. And we, knowingly or not, are moving with it. In everyday life, time feels steady and universal. A second seems to last the same whether we are standing still or moving, whether we are young or old, whether we are on one side of the planet or the other. Our clocks agree with one another. Our schedules align. Time appears to flow like a quiet, invisible river, carrying everyone forward at the same pace. But the universe does not share this assumption. In reality, time does not pass at the same rate everywhere. It does not flow independently of where you are or how you move. Time is shaped by space, by motion, and by gravity. It is not a background feature of the universe. It is part of its structure. Modern physics describes space and time as a single, unified entity. They are not separate ingredients mixed together by convenience. They are inseparable. Change one, and the other responds. This idea is difficult to accept because our senses were never designed to notice it. On human scales, the effects are subtle, but across cosmic distances and extreme speeds, the connection becomes unavoidable. When an object moves through space, it also moves through time. The faster it moves through space, the slower it progresses through time relative to something at rest. This is not a mechanical problem or an error in measurement. It is how the universe is built. Motion changes the way time unfolds. This effect is known as time dilation, and it has been tested repeatedly. Clocks placed on fast-moving aircraft tick slightly more slowly than clocks on the ground. Satellites orbiting Earth must constantly adjust their onboard clocks to stay synchronized with systems on the surface. Without these corrections, modern navigation would quickly drift into error. The universe is not being philosophical here. It is being precise. Numbers whisper more than they speak. The reason this happens lies in the structure of space-time itself. There is a limit to how fast anything can move through space-time, and that limit is the speed of light. No matter how fast you travel through space, your total motion through space-time remains constant. Increase one, and the other must decrease. As motion through space accelerates, motion through time slows. This does not mean time stops or reverses, it simply stretches. A moving observer experiences fewer moments between two events than someone who remains still. Both experiences are valid. Neither perspective is privileged. The universe does not enforce a single, universal clock. Space rarely gives us simple answers. Gravity also affects the flow of time. The stronger the gravitational field, the more slowly time passes. Near massive objects like planets, stars, or black holes, space-time curves more deeply. Clocks closer to these masses tick more slowly than those farther away. This is not a dramatic effect in daily life, but it becomes measurable with precise instruments. Even the difference in altitude between your feet and your head changes the rate at which time passes, though by an amount far too small to notice. These ideas challenge the way we instinctively think about the present moment. We often assume that now is shared across the universe. But there is no single cosmic present. What is happening at a distant star right now depends on who is asking and how they are moving. The universe allows many versions of now, coexisting without contradiction. Silence is also a kind of data. For humans, this realization can feel disorienting, but it can also be quietly comforting. It reminds us that our experience of time, though limited, is not incorrect. It is simply local. Our clocks work because they are meant to describe life on Earth, at earthly speeds, under Earth's gravity. They are not meant to govern the cosmos. When we look up at the night sky, we are not just seeing distant places. We are seeing different moments in time, preserved by the finite speed of light. Some of the stars we see no longer exist. Their light continues to arrive long after their matter has changed or disappeared. The universe is patient in this way. It lets time overlap with itself. Understanding that time is bound to space does not make the universe simpler. It makes it richer. It allows reality to remain consistent even when perspectives differ. It allows motion, gravity, and observation to coexist without conflict. And as we move deeper into this journey, one quiet truth begins to settle in. Time is not something we move through alone. It is something the universe carries with us, gently reshaping itself as we go. At first glance, the speed of light seems like just another number. A large one, certainly, but still a number that belongs to physics textbooks rather than daily life. Yet this single value quietly reshapes our entire understanding of space, time, and motion. No matter how fast you move, no matter which direction you travel, the speed of light in a vacuum remains the same for every observer. This is not an approximation. It is not a technological limitation. It is a fundamental rule of the universe. This idea runs directly against common sense. In everyday experience, speeds add together. A car moving forward feels faster if you are already in motion, A thrown ball gains speed if you are running, but light does not behave this way. Whether you are standing still, riding a spacecraft, or traveling at an enormous fraction of light speed, light always moves away from you at exactly the same rate. The universe enforces this rule without exception. Numbers whisper more than they speak. To preserve this constant, space and time must adapt. They stretch, compress, and reorganize themselves in ways that keep the speed of light unchanged. This is the heart of special relativity. It is not that time and space are distorted as a side effect. They are altered because the universe demands consistency above all else. As an object accelerates toward the speed of light, time begins to slow for that object relative to observers at rest. This slowing is not a malfunction of clocks or a psychological illusion. Time itself expands. Fewer moments pass on the moving clock compared to one that remains stationary. From the perspective of the traveler, everything feels normal. Heartbeats remain steady. Thoughts flow as usual. It is only when compared with someone else that the difference becomes clear. This effect grows stronger as speed increases. At modest velocities, the change is barely detectable. But as motion approaches the speed of light, time dilation becomes dramatic. A journey that lasts years for an observer at rest may feel like months or even days to the traveler. Both experiences are equally real. The universe makes room for both by allowing time to stretch. Space rarely gives us simple answers. Alongside the stretching of time comes the contraction of space. Distances measured in the direction of motion become shorter for the moving observer. This effect, known as length contraction, is subtle and counterintuitive. It does not mean that objects physically compress in their own frame. Instead, space itself adjusts. The universe reshapes distance so that the speed of light remains constant from every viewpoint. For the traveler, the destination appears closer. For the observer at rest, the traveler's clock runs slow. Neither perspective is wrong. Each follows directly from the structure of space-time. Motion changes not just how fast you move, but how much space and time exist along your path. These changes remain hidden in everyday life because human speeds are tiny compared to the speed of light. We are not built to notice them. But in the realm of spacecraft, particles, and cosmic rays, these effects become essential. Without accounting for them, modern physics would collapse into contradiction. As speed continues to increase, another strange effect emerges. The view of the universe ahead of a near light-speed traveler becomes distorted. Light from the front is compressed into a narrower region of the sky, while light from behind spreads outward. Colors shift. Brightness intensifies in the direction of motion. This phenomenon is not an optical trick. It is a direct result of how space-time and light interact at extreme velocities. To someone aboard such a spacecraft, the universe would no longer resemble a familiar star-filled dome. Instead, it would appear concentrated, focused, almost funneled into the direction of travel. Stars ahead would seem brighter and bluer, while those behind would fade and redden. The sky itself would feel reshaped by motion. Silence is also a kind of data. These effects reveal something quietly profound. Space and time are not fixed backgrounds that exist independently of observers. They are relational. They depend on motion, on perspective, and on the paths taken through the universe. There is no single way to describe distance or duration that applies everywhere. This does not mean reality is subjective. It means reality is consistent across perspectives, even when those perspectives disagree. The laws of physics remain the same for all observers, but the measurements they make can differ. The universe does not choose a preferred frame. It allows many viewpoints to coexist without conflict. For humans, this realization carries a subtle emotional weight. It reminds us that our experience of time is not the standard by which the cosmos operates. Our seconds and years are local agreements, shaped by our planet's gravity and our modest speeds. Beyond these familiar conditions, time behaves with greater flexibility. As we imagine traveling faster and faster, approaching the ultimate speed limit of the universe, we are not simply imagining a technical challenge. We are imagining a different relationship with time itself. One in which aging slows, distances shrink, and the night sky transforms in response to motion. And perhaps this is the quiet lesson of special relativity. The universe is not rigid. It is precise, but it is also adaptable. It reshapes space and time to protect its deepest rules, leaving us to discover that even the most familiar concepts are more fluid than they appear. At first, the number sounds almost manageable. Alpha Centauri is about 4.3 light-years away. In the language of astronomy, that is close. It is our nearest neighboring star system, a familiar reference point whenever scientists discuss interstellar travel. But numbers can be deceptive, especially when they describe distances measured not in miles or kilometers, but in years of light. A light year is not a measure of time, it is a measure of distance. It represents how far light travels in 1 year, moving at the maximum speed allowed by the universe. When we say 4.3 light-years, we are saying that even light itself needs more than 4 years to cross that gap. For anything slower than light, the journey stretches far longer. Suddenly, the number feels heavier. Numbers whisper more than they speak. To imagine this journey properly, we must let go of the idea that distance alone defines travel. At relativistic speeds, distance and time are no longer independent. They become intertwined in ways that challenge intuition. A spacecraft capable of approaching the speed of light would experience the journey very differently from observers left behind on Earth. For the crew aboard such a vessel, time would slow. Their clocks would tick more gently. Their bodies would age more slowly compared to those who remained at rest. This is not science fiction. It is a direct consequence of special relativity. Motion alters the flow of time. If the spacecraft traveled fast enough, the crew might experience only a few years or even months on the journey to Alpha Centauri. Meals would be shared. Conversations would unfold. Sleep would come and go. From their perspective, life would continue almost normally. The universe would feel quiet and contained. But back on Earth, time would tell a different story. As the spacecraft sped away, years would pass. Then decades. If the journey extended beyond nearby stars, centuries would begin to accumulate. With enough distance and speed, Earth could move through thousands, then millions of years, while only a small span passed for the travelers. Civilizations would rise and fall. Continents would drift. Species would appear and vanish. The crew, preserved by relativistic time dilation, would remain largely unchanged. Space rarely gives us simple answers. This asymmetry is often called the twin paradox. One twin travels at high speed through space while the other stays behind. When they reunite, the traveling twin is younger. The paradox is not a contradiction in physics. It is a reflection of how space-time responds to motion. The traveler changes direction. They accelerate and decelerate. Their path through space-time is different. Time does not owe symmetry to those who move differently. The return journey reveals the full weight of this reality. Going fast is not enough. To come home, the spacecraft must slow down. Deceleration is not optional. It is the price of arrival. And during this slowing, the accumulated difference in time becomes unavoidable. For the crew, the moment of return would be quietly profound. They would step into a world that no longer belongs to them. Languages might be unrecognizable, landscapes transformed, the sun itself subtly older. Earth would not be waiting. It would have continued on its own path through time. Silence is also a kind of data. This is where the emotional dimension of relativistic travel becomes clear. Interstellar journeys are not just technical challenges, they are temporal separations. Traveling far and fast means leaving your era behind. Distance becomes time, and time becomes loss. Even the journey to Alpha Centauri, modest by cosmic standards, forces us to confront this truth. At conventional speeds, it would take tens of thousands of years. At relativistic speeds, it could be experienced within a human lifetime, but only by disconnecting that lifetime from Earth's timeline. The universe allows the journey, but it does not preserve continuity. There is no way to outrun this trade-off. Faster travel demands greater time dilation. Longer distances amplify the separation. The laws of physics do not forbid interstellar voyages, but they quietly reshape their consequences. Every gain has a cost measured not in fuel alone, but in years left behind. This perspective shifts how we think about exploration. On Earth, explorers return with stories to tell. In deep space, the story continues, but the audience may no longer exist. The farther we go, the more we travel into a future that cannot be shared. And yet, there is something deeply human in this scenario. We have always been willing to trade certainty for curiosity, to step into the unknown, even knowing we may not return to the same world. Relativistic travel simply makes this trade explicit. As we imagine the stars growing closer and Earth fading into memory, we begin to see that time is not merely a backdrop to our journeys, it is the journey itself, unfolding differently depending on how we move through space. And perhaps the quiet lesson here is not about distance or speed, but about belonging. The universe allows us to go far, but it gently reminds us that every path through space is also a path through time, and not all paths lead back to where we began. When we imagine traveling close to the speed of light, it is tempting to think only about engines, fuel, and engineering. Bigger rockets, better materials, smarter navigation. But long before technology becomes the limiting factor, the universe itself begins to resist. Not through force or intention, but through quiet, unavoidable physical laws. At everyday speeds, space feels empty and forgiving. At extreme speeds, that same emptiness becomes something else entirely. One of the most subtle yet profound dangers comes from the cosmic microwave background. This radiation fills the universe uniformly, a faint afterglow left over from the early stages of cosmic expansion. Under normal conditions, it is harmless. It passes through us constantly, unnoticed, carrying information rather than threat. But when a spacecraft approaches the speed of light, perspective changes. Radiation that is gentle and uniform in one frame becomes concentrated and intensified in another. From the viewpoint of a near light-speed traveler, the microwave background ahead is no longer microwaves. It is shifted upward in energy, compressed into higher frequencies. What was once a cold, quiet bath of radiation becomes something far more energetic. Numbers whisper more than they speak. This shift is not dramatic in appearance, but it is severe in consequence. The faster the spacecraft moves, the more intense this radiation becomes in its forward direction. At sufficiently high speeds, it reaches levels that biological tissue cannot tolerate. Shielding helps only to a point. The problem is not exposure time alone, but energy density itself. The universe is not attacking. It is simply being observed from a different frame. Interstellar dust presents a similar challenge. Space may seem empty, but it is not perfectly so. Between stars drift tiny grains of matter, often no larger than smoke particles. At conventional speeds, these grains are insignificant. At relativistic speeds, they become dangerous. Energy depends on velocity. As speed increases, even a minuscule particle carries enormous kinetic energy. A dust grain encountered at near light speed does not behave like dust. It behaves like a concentrated burst of energy. The impact is not a collision in the everyday sense. It is a localized release of force capable of damaging or penetrating material. Silence is also a kind of data. These risks cannot be solved simply by building stronger hulls. Each increase in speed raises the energy involved in every interaction with the environment. Shielding grows heavier. Structures become more complex. Eventually, the energy required to protect against these effects rivals the energy required to move in the first place. This is where the distinction between engineering limits and physical limits becomes clear. Technology can improve, materials can be refined, designs can evolve. But the transformation of radiation and matter at extreme velocities is not a problem waiting for a clever solution. It is a consequence of fundamental physics. Space rarely gives us simple answers. The universe enforces consistency across all frames of reference. It does not allow shortcuts that violate its deepest rules. As velocity increases, so do the consequences of motion. This balance is not punitive, it is structural. The same laws that allow time dilation and length contraction also amplify radiation and energy transfer. From a human perspective, this can feel discouraging. We are used to solving problems by iteration and innovation. But some barriers are not walls to be climbed. They are boundaries that define what motion in itself means. Understanding these risks reshapes how we think about exploration. It suggests that interstellar travel is not merely about reaching destinations faster. It is about choosing trajectories that remain compatible with life and structure. Slower paths may be safer, even if they demand patience measured in generations rather than years. And yet, this does not diminish the wonder of the universe. If anything, it deepens it. The same laws that limit us also make the cosmos intelligible. They ensure that space behaves consistently, that energy is conserved, that cause and effect remain connected. As we imagine journeys at the edge of what is physically possible, we are reminded that speed is not free. Every increase carries a cost written into the fabric of space-time itself. And perhaps the quiet lesson here is this. The universe does not forbid us from moving fast. It simply asks us to understand what fast truly means. As we move beyond the familiar neighborhood of planets and orbits, space does not suddenly become uniform or empty. It changes gradually, layer by layer, revealing structures that are easy to overlook because they do not shine brightly or announce themselves. Interstellar space is not a void. It is a medium, thin and subtle, shaped by ancient explosions and long, quiet processes. Our sun does not drift through a neutral background. It travels within a region known as the local bubble, a vast cavity of hot, low-density gas carved into the surrounding interstellar medium. This bubble spans hundreds of light-years and is thought to be the result of multiple supernovae that occurred millions of years ago. These explosions swept away cooler gas, leaving behind a region filled with energetic particles and faint plasma. From Earth, this environment feels invisible, yet it quietly influences everything that moves through it. The solar system is embedded within this bubble, carried along as the sun orbits the center of the galaxy. We are not isolated. We are passengers inside a structure shaped by stellar death long before humanity existed. Numbers whisper more than they speak. Beyond the local bubble lie interstellar clouds, regions where gas and dust are slightly more concentrated. These clouds vary in temperature and density, ranging from cold molecular clouds where stars form to warmer, more diffuse regions. None of them are solid or sharply defined. Their boundaries are soft, shifting, and permeable. But they are not harmless emptiness. Interstellar clouds contain particles, radiation, and magnetic fields. For a spacecraft traveling between stars, these environments matter. Even at modest speeds, long exposure to interstellar material affects surfaces, instruments, and trajectories. Over vast distances, small interactions accumulate. Space does not need to be dense to be influential. Silence is also a kind of data. This becomes even more important as we consider travel on galactic scales. The Milky Way is often depicted as a bright spiral filled with stars, but this image hides an essential truth. Most of the galaxy's volume contains very little matter. Stars cluster in disks, arms, and central regions, while enormous expanses remain sparsely populated. As one moves toward the outer regions of the galaxy, star density drops sharply. The edge of the galaxy is not a wall or a boundary line. It is a gradual thinning. Stars become more distant from one another. Gas becomes more diffuse. Encounters grow rare. The galaxy fades rather than ends. Space rarely gives us simple answers. This gradual transition challenges the way we think about cosmic borders. We tend to imagine edges as places where something stops. In reality, the universe prefers gradients. There is no moment when the Milky Way suddenly ceases to exist. There is only a slow transition from structure to sparsity, from brightness to darkness. Beyond the visible edge lies the galactic halo, a vast region containing dark matter, old stars, and tenuous gas. It extends far beyond the familiar spiral arms. Even here, the galaxy's influence persists through gravity and motion. The idea of leaving the galaxy entirely becomes less about crossing a line and more about drifting beyond influence. For humans, this perspective reshapes the meaning of distance. Traveling farther does not always mean encountering something new. Often it means encountering less. Fewer stars, fewer signals, longer stretches of quiet motion through environments that change slowly over millions of years. And yet, these regions are not empty in a scientific sense. They preserve records of the galaxy's past. The composition of interstellar gas tells stories of previous generations of stars. The shape of the halo reveals the presence of unseen matter. Absence itself becomes information. Numbers whisper more than they speak. From within the local bubble to the fading outskirts of the galaxy, space teaches us patience. It does not reveal itself through dramatic transitions, but through accumulation. Small changes spread across enormous distances define the large-scale structure of the cosmos. As we imagine moving farther and farther from home, one quiet truth emerges. The universe does not separate places with sharp borders. It connects them through gradual change. And in that slow fading, we begin to understand that distance is not just measured by how far we travel, but by how gently the familiar dissolves into the unknown. From within our galaxy, the universe can feel expansive yet approachable. The Milky Way contains hundreds of billions of stars stretched across a disk more than 100,000 light-years wide. Even this scale already exceeds anything humanity can meaningfully traverse. But when we look beyond it, the challenge shifts from difficult to fundamentally unreachable. Intergalactic travel is not simply a longer version of interstellar travel. The distances involved are not measured in years or even lifetimes, but in spans of time that dwarf the entire history of our species. The nearest large galaxy, Andromeda, lies more than 2 million light-years away. Even at speeds that approach the limits allowed by physics, such a journey would demand conditions and consequences far beyond any realistic human framework. Numbers whisper more than they speak. The vastness between galaxies is not filled with helpful pathways or intermediate stops. It is an ocean of extreme emptiness, punctuated only by faint gas, dark matter, and the slow curvature of space-time itself. A spacecraft leaving the Milky Way would not simply be traveling farther. It would be leaving behind the gravitational, material, and temporal environment that makes stars and planets familiar. But distance alone is not the greatest obstacle. The universe itself is changing while we imagine these journeys. Space rarely gives us simple answers. The universe is expanding, and that expansion is accelerating. This is not an explosion from a central point, but a stretching of space everywhere at once. On large scales, galaxies are moving away from one another, not because they are traveling through space, but because the space between them is growing. The farther a galaxy is from us, the faster it recedes. This acceleration introduces a profound limitation. There exists a cosmic horizon beyond which galaxies recede faster than light relative to us, not by violating physical laws, but because the expansion of space itself carries them away. Light emitted by these galaxies will never reach us, no matter how long we wait. They are not hidden. They are simply beyond causal contact. Silence is also a kind of data. This means that the universe contains regions we can never observe, never interact with, and never reach. Even if a civilization possessed extraordinary technology and infinite patience, there are destinations that cannot be visited and messages that cannot be exchanged. The expansion of the universe places an absolute boundary on what is accessible. For journeys that aim to return, the limitation is even stricter. A round trip requires that the traveler remain within the region of space that stays gravitationally and causally connected. Beyond a certain distance, the outward expansion overwhelms any attempt to come back. The path outward may be possible. The path home may not exist. This is not a technical failure. It is a geometric feature of space-time on the largest scales. As time passes, this horizon grows more restrictive. Galaxies that are visible today will slowly fade from view. Their light will stretch to longer wavelengths, becoming weaker and harder to detect. Eventually, many will disappear entirely from the observable universe. Not because they vanish, but because space has carried them beyond reach. Numbers whisper more than they speak. From the perspective of distant future observers, the universe may appear far smaller than it does today. Only nearby galaxies, bound together by gravity, will remain visible. The broader cosmic web will dissolve into darkness, leaving behind isolated islands of matter surrounded by expanding emptiness. For humanity, this realization reframes exploration. There is no moment in the future when we will stand at the edge of the universe and look outward. The universe does not end. Our access to it does. This does not diminish the significance of what we can observe now. On the contrary, it makes the present era remarkable. We live at a time when the universe is still visible across vast distances, when ancient light continues to arrive from galaxies billions of years old. Our telescopes capture a richness that future observers may never see. Space rarely gives us simple answers. There is a quiet humility in knowing that some destinations are not meant to be reached. The universe does not arrange itself around our ambitions. It unfolds according to its own rules, allowing understanding without granting control. Yet within these limits, meaning remains. The galaxies that drift beyond our horizon do not cease to exist because we cannot see them. They continue their histories, forming stars, evolving structures, and carrying their own deep time forward. As we imagine traveling beyond the Milky Way, we are reminded that exploration is not always about arrival. Sometimes it is about understanding where the paths end and why. And perhaps this is the calm truth revealed at this scale. The universe invites us to look outward, to learn, to wonder. But it also teaches us that not every journey is measured by distance traveled. Some are measured by the clarity gained when we accept the boundaries written into the fabric of space itself. When confronted with the immense distances and limits imposed by space and time, it is natural to imagine shortcuts. Concepts like space-time tunnels, wormholes, and faster-than-light travel capture the imagination because they promise escape from constraints that otherwise seem absolute. These ideas appear frequently in stories and speculation, offering ways to cross cosmic distances without paying the full cost measured in years or centuries. From a scientific perspective, these concepts are not dismissed lightly. They emerge from mathematical extensions of known theories, particularly general relativity. Under certain conditions, space-time can curve in ways that suggest the possibility of shortcuts connecting distant regions. Wormholes, in theory, are solutions to the equations that describe gravity. They are not inventions of fiction. They arise naturally on paper. Numbers whisper more than they speak. But mathematical possibility is not the same as physical reality. No observational evidence has ever confirmed the existence of traversable wormholes or space-time tunnels. More importantly, keeping such structures stable appears to require forms of energy that have never been observed in nature. These hypothetical energies would need properties unlike any known matter, including the ability to produce negative energy density. Even if such exotic conditions were possible, the scale of energy required would be immense. Not merely large by human standards, but comparable to the mass energy of stars or entire planetary systems. The universe may permit such configurations in principle, but it does not offer them freely. Space rarely gives us simple answers. Faster-than-light travel presents similar challenges. The speed of light is not just a limit on motion, it is a cornerstone of how causality operates. Allowing objects or information to exceed this speed risks breaking the consistent order of cause and effect. While certain theoretical frameworks explore ways around this, they consistently encounter the same barrier. The energy demands become effectively unbounded. There are proposals within physics that attempt to bend, rather than break, these rules. Concepts such as space-time compression or engineered expansion aim to move space itself rather than objects through it. In these scenarios, a vessel remains locally at rest while the space around it contracts ahead and expands behind. The mathematics does not forbid such solutions. Silence is also a kind of data. Yet once again the cost reappears. The required energy densities are extraordinary. The configurations are unstable. The conditions demand precision and control beyond anything conceivable with known physics. These are not engineering problems waiting for refinement. They are indicators of fundamental imbalance. The universe does not prohibit imagination. It allows speculation, but it responds to physical attempts with strict accounting. Every apparent loophole carries a price that restores consistency. This pattern appears repeatedly in physics. When a theory suggests a way around a limit, deeper analysis reveals a hidden cost. Energy increases, stability decreases, uncertainty grows. The universe balances its equations without exception. Numbers whisper more than they speak. From a human point of view, this can feel like resistance, but it is better understood as coherence. The same laws that constrain us also protect the structure of reality. They ensure that time flows in a consistent direction, that cause precedes effect, and that information remains bounded by space. The absence of easy escapes does not diminish the universe. It gives it character. It reminds us that exploration requires patience, adaptation, and respect for limits that were not designed for convenience. There is a quiet honesty in this. The universe does not promise shortcuts. It offers understanding instead. It invites us to learn how things work, not how to bypass them. As we move forward in this journey, we begin to see that the true challenge is not distance alone. It is accepting that some paths remain theoretical, not because we lack creativity, but because the cosmos demands balance. And perhaps this is the calm lesson here. The universe does not forbid us from dreaming of escape. It simply asks us to recognize the cost and to decide whether understanding itself might be the deeper destinations. Imagine a journey that lasts only a short while for those aboard, yet stretches across billions of years for everything left behind. The travelers return, their bodies largely unchanged, their memories intact. But the place they come back to is no longer the world they once knew. This is not a story of sudden destruction. It is a story of quiet, inevitable change. Earth's future is closely tied to the life cycle of the Sun. Our star is stable now, calmly converting hydrogen into energy. But stars do not remain unchanged forever. Over billions of years, the Sun will slowly grow brighter and warmer as its internal balance shifts. This increase in energy is gradual, measured not in dramatic events, but in steady accumulation. Numbers whisper more than they speak. Long before the Sun reaches the end of its life, its growing luminosity will begin to affect Earth. Higher temperatures will alter the planet's climate beyond recovery. Oceans will evaporate, first thinning, then retreating entirely into the atmosphere. Water vapor, a powerful greenhouse gas, will trap heat more effectively, accelerating the warming process. This feedback is not violent. It is persistent. As surface temperatures rise, the planet's crust will soften. Tectonic activity will slow. Chemical cycles that once supported life will break down. The familiar blue of the oceans and the green of living landscapes will fade. Earth will become a dry, hostile world, more closely resembling the inner planets than the living sphere we recognize. Silence is also a kind of data. This transformation does not require an external catastrophe. No asteroid impact is needed, no explosion from space. It unfolds as a natural consequence of stellar evolution. The Sun simply continues doing what stars do. Earth responds according to physical law. Eventually, the Sun will enter a red giant phase, expanding outward as it exhausts its core fuel. Whether Earth is engulfed or merely scorched depends on complex interactions between mass loss and orbital dynamics. Either outcome leads to the same result. The planet, as a home for life, will be gone. Space rarely gives us simple answers. From a human perspective, it is tempting to label this as tragedy. But in cosmic terms, it is neither tragic nor exceptional. Planets form, planets change. Habitable conditions arise, persist for a time, and fade. Life is not promised permanence, it is granted opportunity. Understanding this future reframes how we think about survival and legacy. The disappearance of life on Earth is not a failure of biology or intelligence. It is a reminder that stability is always temporary. Even worlds that seem permanent exist on borrowed time. Numbers whisper more than they speak. If travelers were to return after billions of years, they would not witness ruins. They would see transformation carried to its conclusion. A planet reshaped by heat and time. A sun entering a different stage of existence. The absence of life would not feel like loss in the usual sense, it would feel like silence. Silence is also a kind of data. This perspective invites humility rather than fear. It places human history within a much longer narrative. Our civilizations, cultures, and memories occupy only a brief interval in Earth's story. That does not diminish their meaning. It clarifies it, in recognizing that Earth's end comes not from violence but from continuity. We learn something essential about the universe. Change is not always abrupt. Often it arrives quietly, through processes that never pause or reverse. And perhaps this is the calm truth carried by deep time. What matters is not how long something lasts, but that it existed at all, shaping and being shaped by the universe for a while before yielding to the next chapter. For most of cosmic history so far, stars have been the universe's primary storytellers. They ignite from clouds of gas, shine steadily for millions or billions of years, and shape everything around them. Their light defines structure. Their gravity gathers matter. Their deaths seed space with the elements needed for planets and, for a time, for life. When we look up at the night sky, we are witnessing an era dominated by stars. But this era is not permanent. Stars shine because they consume fuel. Deep in their cores, nuclear reactions convert mass into energy, releasing light and heat into space. This process is remarkably efficient, but it is not endless. Every star, no matter how large or long-lived, carries within it a finite supply of usable fuel. Once that supply is exhausted, the star must change. Numbers whisper more than they speak. Across the universe, stars are slowly aging. Some burn quickly and die young. Others, like our sun, burn gently and endure for billions of years. But none escape the same conclusion. As time stretches forward, fewer new stars are born. Gas clouds thin, star formation slows. The balance gradually shifts from creation to exhaustion. As stars run out of fuel, their light fades or transforms. Massive stars collapse or explode, leaving behind neutron stars or black holes. Smaller stars shed their outer layers and contract into white dwarfs. These white dwarfs no longer generate energy through fusion. They shine only by releasing the residual heat left over from their earlier lives. Space rarely gives us simple answers. White dwarfs are quiet objects. Dense, compact, and stable, they can persist for enormous spans of time. But even they do not last forever. Over trillions of years, they slowly cool, radiating away their remaining warmth. Eventually, they fade into what physicists call black dwarfs. These are theoretical objects, cold and dark, marking the final state of stellar remnants that were never massive enough to collapse further. The transition from white dwarf to black dwarf is so slow that none exist yet. The universe is still too young, but given enough time, they will come to dominate the stellar population. The night sky, once filled with points of light, will grow darker. Silence is also a kind of data. As stars disappear, so do the environments they sustain. Without stellar radiation, planets lose heat, chemical reactions slow, energy gradients flatten, matter becomes increasingly inert. The universe does not stop existing, but it becomes less dynamic. In this late epoch, the opportunities for complexity narrow. Matter still exists, particles still interact, but the conditions that allow structure to build and persist grow rare. Life, as we understand it, depends on energy flow. When stars fade, those flows weaken. Numbers whisper more than they speak. This does not mean that the universe becomes empty. It becomes quiet. Black dwarfs, neutron stars, and black holes continue to move through space, bound by gravity. Occasionally, remnants may interact, a collision, a merger, a brief release of energy. But these events become increasingly infrequent as distances grow and matter thins. From a human perspective, it is difficult to imagine a universe without stars. Light has always been our reference, Our calendars, our myths, our sciences are built around it. To think of an era when starlight is no longer common feels unsettling. But on cosmic timescales, this transition is as natural as nightfall. Space rarely gives us simple answers. The end of the stellar era is not marked by a single moment or event. It unfolds gradually, unevenly, across unimaginable spans of time. Some regions will retain stars longer than others. Isolated pockets of light may persist while most of the universe grows dim. The process is not synchronized. It is statistical. What remains after the stars fade is matter stripped of its most dramatic expressions. Atoms endure. Particles persist. The universe retains memory in its structure, even as its energy declines. Silence is also a kind of data. This future challenges our instinct to equate brightness with significance. The universe does not end when the lights go out. It continues, governed by the same laws but operating in a quieter register. Complexity gives way to stability. Activity yields to endurance. In some sense, this era reflects a different kind of survival. Matter persists not by transforming rapidly, but by remaining intact. White dwarfs and black dwarfs do not compete or consume. They simply exist, cooling slowly, carrying the record of what once burned brightly. Numbers whisper more than they speak. As we consider the end of the stellar era, we are reminded that change does not always announce itself with spectacle. Sometimes it arrives through patience, through exhaustion rather than violence, through the steady completion of processes that began long before we were here. And perhaps this is the calm truth at the close of this chapter. Light is precious because it is temporary. Stars matter because they do not last. And in the long arc of the universe, even their fading becomes part of a larger, quieter story that continues to unfold. As the universe ages and stars fade, gravity continues its quiet work. Matter drifts, collisions become rarer, and energy spreads thin. In this long future, black holes remain among the most enduring structures. They are not sudden intruders into cosmic history, but natural outcomes of stellar evolution and gravitational collapse. Over time, they come to play a central role in how matter and energy are stored and released. Black holes are often described as destructive, but a calmer view reveals something different. They are endpoints. When massive stars exhaust their fuel and collapse, or when dense remnants merge, gravity overwhelms all other forces. Matter falls inward and becomes bound within a region from which light cannot escape. This process does not erase matter. It rearranges it into a new, extremely compact state. Numbers whisper more than they speak. In the distant future, as stars cease to shine and white dwarfs cool, black holes persist. They are among the last objects capable of interacting meaningfully with their surroundings. Gas, stellar remnants, and even other black holes may gradually spiral inward. In this sense, black holes become the final resting places of matter, gathering what remains as the universe grows quieter. This does not mean black holes consume everything indiscriminately. Their influence is precise. Matter must pass close enough to be captured. Vast regions of space remain untouched. But over long timescales, gravity favors accumulation. Given enough time, black holes tend to grow. Space rarely gives us simple answers. Beyond their role as collectors of matter, black holes also serve as reservoirs of energy. When matter falls into a black hole, it does not disappear quietly. As it spirals inward, it heats up, releasing energy in the form of radiation and motion. In earlier cosmic epochs, this process powers quasars and active galactic nuclei, some of the brightest phenomena in the universe. In later eras, as stars fade, such activity becomes rarer but not meaningless. Each merger, each infall, represents a release of energy that momentarily interrupts the universe's gradual cooling. These events are not frequent, but they are significant. They mark transitions. They punctuate long stretches of stillness. Silence is also a kind of data. As the stellar era ends, the universe enters what can be called the era of black holes. This is not an age of chaos or destruction, but one of slow consolidation. Black holes dominate the remaining mass. Galaxies stripped of their stars become collections of remnants orbiting massive central objects. The most dramatic events of this era are mergers. When two black holes approach one another, they spiral inward, losing energy through gravitational radiation. These waves ripple through space-time, carrying information about mass and motion. For a brief moment, the universe speaks clearly, announcing the union of extreme objects. Numbers whisper more than they speak. Gravitational waves are not loud in the human sense. They do not shake planets or tear matter apart at a distance. But they represent one of the last large-scale ways the universe can move energy around. As time progresses, even these events become rare. Distances grow, encounters diminish. Eventually, black holes become isolated. Each one carries within it the mass of countless stars and remnants, compressed into a region smaller than a city. They orbit slowly, influenced by expansion and by the faint gravitational pull of distant structures. The universe grows increasingly simple in composition, though not in history. Space rarely gives us simple answers. It is tempting to think of black holes as endings, but they are better understood as transitions. They do not stop physics from operating. They concentrate it. They preserve matter in forms that can persist for unimaginably long times. In doing so, they delay the final quieting of the cosmos. From a human perspective, black holes feel alien and extreme. But in the long narrative of the universe, they are consistent. They follow the same rules that govern stars, planets, and particles. Gravity gathers, energy disperses, structure evolves. Silence is also a kind of data. In the era of black holes, the universe is not empty. It is restrained. Activity is localized. Change occurs slowly. Yet even in this quiet phase, information remains encoded in motion, in mass, in the curvature of space-time. Understanding the role of black holes shifts our sense of cosmic time. The end of stars does not mark the end of structure. It marks a change in how structure persists. Brightness gives way to density. Fusion gives way to gravity. Light yields to curvature. Numbers whisper more than they speak. As we reflect on this stage of the universe, we see that endurance does not require activity. Black holes endure by being stable, by holding on to what remains. They are not the universe's final word, but they carry the conversation forward into deeper time. And perhaps this is the quiet truth of black holes. They do not dominate because they are violent. They dominate because, in a universe that grows ever calmer, gravity is patient, and patience is enough. For a long time, black holes were thought to be eternal. Once formed, they seemed destined to persist forever, silently holding on to everything that crossed their boundaries. In a universe where stars fade and matter disperses, black holes appeared to be the final survivors, immune to decay and untouched by time. But the universe rarely allows absolutes. In the 1970s, a quiet idea changed this picture. It suggested that black holes are not perfectly black and not truly permanent. At the edges of a black hole, where gravity is extreme and space-time curves sharply, quantum effects begin to matter. This boundary, known as the event horizon, is not a solid surface. It is a region where the rules of physics overlap in subtle ways. According to this understanding, black holes emit a faint form of radiation, now known as Hawking radiation. It arises from quantum fluctuations near the event horizon, where pairs of particles briefly appear and disappear. Under certain conditions, one particle escapes while the other falls inward. To an outside observer, it appears as though the black hole has emitted energy. Numbers whisper more than they speak. This radiation is incredibly weak. For black holes formed from stars, the amount of energy released is far smaller than the cosmic background that surrounds them. They absorb far more than they emit, at least in the current universe. But over immense spans of time, as the universe cools and grows quieter, this balance shifts. As surrounding matter and radiation thin out, black holes begin to lose more energy than they gain. Slowly, almost imperceptibly, they start to shrink. This process is not dramatic. It does not resemble evaporation in the everyday sense. It is a gradual reduction in mass, stretched across timescales so long they defy ordinary comparison. Space rarely gives us simple answers. The larger the black hole, the slower this process unfolds. Supermassive black holes containing the mass of millions or billions of stars will endure for extraordinarily long periods. Their lifetimes extend far beyond the era of stars, beyond the cooling of white dwarfs, and beyond the merging of galaxies, but even they are not exempt. Given enough time, every black hole will lose its mass entirely. The universe allows no structure to remain unchanged forever. Even the most extreme concentrations of gravity participate in the slow redistribution of energy. Silence is also a kind of data. The final stages of a black hole's life are thought to be subtle rather than explosive. As mass decreases, the rate of radiation increases, but this occurs only near the very end. After durations that exceed the current age of the universe by staggering factors. These are events not meant to be witnessed but inferred. This realization carries a quiet symmetry. Black holes form through collapse, gathering matter and energy into the smallest possible volumes. They end through dispersal, returning that energy to space in a diffuse, nearly uniform way. Gravity concentrates. Quantum effects release. The universe balances itself over deep time. Numbers whisper more than they speak. For humans, the idea that black holes are temporary can feel surprising. We often look for permanence in the cosmos, something that endures when everything else fades. But the universe does not preserve by freezing. It preserves by transforming. Black holes are not failures of physics. They are part of its long-term consistency. Their eventual evaporation ensures that energy continues to spread, that no region remains permanently isolated, and that the universe moves steadily toward greater uniformity. Space rarely gives us simple answers. In this light, the mortality of black holes is not a loss. It is a completion. It ensures that even the deepest wells of gravity participate in the same slow story as everything else. Nothing is exempt from time, not even time's most extreme distortions. As we approach the deepest future of the universe, this understanding becomes essential. The cosmos does not end with a final structure standing alone. It continues by letting every structure, no matter how dense or powerful, release its hold. And perhaps this is the calm truth of this chapter. Endurance in the universe is never about lasting forever. It is about lasting long enough to pass something on, before yielding, gently, to the quiet that follows. As the universe moves beyond the era of stars and black holes, it enters a phase governed not by dramatic events, but by patience. Structures that once seemed permanent begin to change in ways so slow that they are almost impossible to imagine. This is the domain of deep time, where even the most stable forms of matter are no longer guaranteed to endure. At the foundation of all visible structure lies the proton. Protons form the nuclei of atoms, anchoring chemistry, matter, and solidity itself. For a long time, they were assumed to be absolutely stable. Nothing in everyday experience suggests otherwise. Protons persist through stars, planets, and living bodies without apparent decay. Yet some theories in particle physics suggest a different possibility. According to these models, protons may not be eternal. They may decay, transforming into lighter particles over extremely long timescales. This process, known as proton decay, has never been observed. Experiments have only established lower limits on how long a proton might survive. Those limits already exceed 10 trillion years. Numbers whisper more than they speak. If proton decay is real, its consequences unfold slowly and universally. Atoms would eventually lose their nuclei. Molecules would fall apart. Solids would dissolve into radiation and elementary particles. This would not resemble destruction in any recognizable sense. There would be no collapse, no explosion, no sudden disappearance. Matter would simply lose its ability to remain matter. Even without proton decay, change continues. Over immense spans of time, bound systems gradually lose energy. Orbits decay. Interactions become rarer. Structures that depend on precise balances weaken as energy spreads more evenly throughout space. Complexity fades not because it is destroyed, but because it can no longer be sustained. Space rarely gives us simple answers. As black holes evaporate and particles drift apart, the universe approaches a state of extreme uniformity. Temperature differences diminish. Energy gradients flatten. The conditions that once allowed motion, chemistry, and structure grow scarce. What remains is a thin distribution of particles and radiation, stretched across an ever-expanding volume. In this far future, photons dominate. Light, once emitted by stars and galaxies, has been stretched by cosmic expansion to longer and longer wavelengths. Energies drop, frequencies slow. Eventually, the universe becomes a near-uniform sea of low-energy photons, punctuated by a few isolated particles drifting through vast distances. Silence is also a kind of data. This outcome is often described as heat death, but the term can be misleading. Nothing actively dies. Instead, the universe settles. It reaches a condition where no useful energy remains to drive change. Without gradients, there is no work to be done. Without work, there is no evolution in the familiar sense. Time continues to pass, but nothing meaningful happens. Numbers whisper more than they speak. From a human perspective, this future feels empty and cold. But from a physical perspective, it is simply equilibrium extended across space. The laws of physics still apply. Particles still exist. But the universe has exhausted its capacity for novelty. It is important to recognize how far removed this state is from anything we experience now. The timescales involved exceed the current age of the universe by orders of magnitude that defy intuition. These are not futures we will witness, but futures implied by consistency. They are conclusions drawn from extending known laws forward, patiently and without drama. Space rarely gives us simple answers. The idea that everything eventually dissolves can feel unsettling. We are accustomed to thinking of matter as solid, of atoms as reliable, of existence as something that endures. But deep time reveals a different pattern. Stability is always conditional. Persistence is always temporary. And yet, there is a quiet coherence in this ending. The universe begins in a state of high density and contrast. Over time, it spreads, smooths, and equalizes. Structure emerges. flourishes briefly, and then fades. Nothing is singled out for special preservation. Everything participates in the same long arc. Silence is also a kind of data. In the end, the universe does not collapse into nothingness. It becomes almost perfectly uniform. Differences disappear. Motion slows to irrelevance. The cosmos remains, vast and calm, carrying within it the faint traces of everything that once occurred. Perhaps this is the final lesson of deep time. Existence is not defined by permanence, but by participation. Matter mattered because it formed stars, planets, and moments of awareness. When those moments pass, the universe does not mourn. It remembers them only in the subtle distribution of energy that remains. And in that quiet, evenly spread sea of photons, the story of the universe is not erased. It is completed gently, without urgency, resting in a state where nothing more needs to happen.